All right. Yeah, thanks for staying here throughout. Yeah, I kind of ate, I think, the time for the break. But yeah, we now have this session, my last session, I guess, on motion forecasting. Give me 1 second. Oh. Yeah, as we saw before, basically, motion forecasting or prediction is this reasoning kind of in the middle of the stack, if you will, where we, given kind of our perception of the world, we try to estimate what's going to happen in the future. I guess contrary to perception, this is not a thing you can try to get perfect at, because you really, there is a lot of latent variables that you don't observe about what's going to happen in the future. So it's more about how you model the uncertainty, in my opinion, rather than, or maybe both, how accurate you can be and how well you can model the uncertainty. There are things like this is probably illegal U-turn done by this vehicle here, or you can see the interactions down the road there, kind of going over a vehicle that's waiting for a left turn. So it's a very complex interaction graph. The agenda for this session is to talk a bit about the task itself. Then how do we, similar to the perception, like kind of how do we encode the scene to do reasoning? And then how do we actually model the future in terms of different paradigms or task formulations as well as representations? Cool. So yeah, about the task, I guess really quickly, some of the main challenges. We don't really get to see everything to start with, right? Like perception won't be perfect essentially. We'll talk a bit about joint perception and prediction models here, which I think is a better fit than just propagating, basically separating the outputs from perception into prediction. But anyway, basically, you don't get to observe everything perfectly. Like, for example, for that vehicle behind, we only see a bit of it. We also don't know what they want to do. Like other vehicles might want to left turn or go straight here, depending on the route, which we don't have any knowledge about. And finally, let's say on an intersection like this, there's some negotiation there going on about who's going to go first and who's going to go after. So the classical approach to this problem is to essentially use a tracker, like I talked earlier in the previous session, and unroll the tracker state. So with some kinematic model, right? We can assume either they are keeping constant velocity or a constant turn rate and acceleration model, or if the high definition map is available, they will follow the center lines, for example. That's something it's typically done in these more traditional stacks. So that's great because it allows us to incorporate our prior knowledge and doesn't need a lot of data. It's fast, but it cannot really capture the diversity of the real world. Like you can see there, those are the predictions versus the ground truth for different pedestrians. And for the ones that are going straight, works great. But for the ones that are doing something slightly different, then it does not. Cool. So basically, the field moved from that to doing ML-based, machine learning-based prediction, but within the same kind of framework. So we have these tracks as input, basically the past states of the objects that our tracker has been able to track, as well as the high definition map. Then we put a neural network and we output future predictions. However, here, if there's some noise in the input, detections and tracks, then it will propagate to prediction, right? It will be really hard to predict a good trajectory for something that we haven't even tracked well. There's also some redundant computation, like we've extracted features to understand these vehicles and how they are moving, and probably we need similar features to do prediction, but now we are separating that into two separate models, which is just redundant computation. And overall, it's a complicated system, hard to train, many dependencies. If the detection team changes something, then the prediction team will have to adjust. And so it's a lot of overhead. Very hard to get right. So instead, what we can do is this more joint perception and prediction. And essentially, we get, instead of getting the tracks as input, we now get temporal sensor data as input. So you can get multi-sweep LiDAR, for example, there. You could also use memory like we saw in the previous presentation. And the idea is that this will output both the current state of the world as well as the future state of the world. And we'll see later in the presentation, in this section, some approaches that really unify these two. And it doesn't need to be necessarily bounding boxes and trajectories. Here we see basically, this is the same model I was showing earlier, but earlier I was showing the perceptions only. And here we can also basically forecast. What you are seeing here is the model forecasting into the future. I'll cover it in more detail as well later. So yeah, now let's get into how we can actually understand the scene. So as I was talking about before, the first methods basically take these tracks, right, of the actors, these trajectories. Then we can encode these past trajectories, which is what we are gonna see how to do now, and then do have some decoder which we'll cover later. And these trajectory encoders can be like, it's basically what we get as input is a sequence of waypoints, right? Perhaps with some uncertainty, different features that the tracker might give us, but essentially it's like a sequence of waypoints or states over time. And this can be basically, we can use convolutional neural networks, recurrent neural networks, or transformer, any sequence model basically to extract features from it. This is typically super fast on the prediction side because the trajectories are low dimensional, but it has very limited expressivity, right? Like everything, all the information that has already been lost by this point is huge. So an alternative, as I was saying earlier, is this multi-sweep LiDAR. And what we are doing here is we are taking multiple LiDARs over time, I think the last 5, and coloring them with the basically time those LiDAR points were captured. And you can see, for example, for this object, right, you can very clearly see actually like its movement. And not only that, this input has already kind of attached to it, if you will, like kind of how uncertain we are, or how certain we can be based on the observations that we are getting, right? We are not just getting that we thought this object did this trajectory. We are actually getting the points, so we can reason about, oh, we didn't have many observations, so I'm going to be more uncertain in my predictions, or I had a lot of observations and it's super clear what's going to do. So how can we, well, the way we can put this together is essentially, like we saw earlier, we can, for example, voxize it in bird's eye view. It could be sparse, it could be dense. We get this feature map, and then from the feature map, we can do object detection, for example. And around the object locations, we can extract certain features and pull them. And from here, we essentially can get an agent feature vector that is kind of the embedding for each agent. From this, the simplest form of prediction, I guess, is taking these agent feature embeddings, passing them through an MLP, and that will give you a future trajectory, right? And the future trajectory here can be as simple of predicting a 2 times t vector, which is like the 2 coordinates x and y in bird's eye view, times t time steps, which is like the amount of time that you want to predict into the future. And this is like CVPR 2018 was the first paper that did something like this. And these are very short range predictions, and it's not great, but the field has advanced a lot since then. And the same ideas with new architectures and the new loss functions can work very well today. Cool. So I won't talk too much about the high definition map. We already covered it in perception. So this is just a quick recap for those that joined now. But basically, the map can be represented in a sparse way through this set of vectors, basically. And we can encode it with any sequence-to-sequence model, like graph neural network or transformer, and learn rich node features, basically. And then we will be able to use these learned features downstream for prediction, like we'll see in a bit. And finally, there's these actor-to-actor interactions that are everywhere in the scene. So in this 4-way stop intersection, for example, based on the past, we cannot really tell what's going to happen. Here, it's more about knowing the rules, like maybe they will yield to the right vehicle, depending, I guess, where. And also just sort of doing relational reasoning to try to understand, maybe if this object is moving a little bit, that means it's going to go and the other one's going to yield. But anyway, it's going to be a very uncertain prediction. And so, yeah, we are talking basically about this point, like we've already extracted agent features, and now we are trying to do some interaction reasoning between the different agents that we've perceived in the scene. So how can we do that reasoning? One way is with graph neural networks. Let's say if every agent is a node in this graph, and then we can assume a fully connected adjacency matrix to basically reason about all the connections between them. Basically, we can extract features like those agent features will become node features in this graph, right? And then we can exchange messages between them, for example, with an MLP. Then all the messages incoming to a node can be pooled with a permutation invariant pooling, like max pooling or average pooling, any pooling mechanism. And finally, we can update the node state of every node. This is just showing one for sort of visually explaining it, but this happens in parallel for all nodes. They can all be updated with a residual connection or with a gated recurrent unit, for example. And the same can be done, of course, with transformers. Transformers are kind of a special case of graph-neural networks in which the message and aggregation are fused into this dot product attention. So basically, dot product attention is taking care of which messages, basically weighting the messages from incoming connections. Cool. So now let's see one example of how to put this together. This is a paper that we released on arXiv a week ago, I think. But basically, on the left, you can see we have these object queries and poses volume. So it's going to be a bit abstract, but basically it has 3 dimensions. There's an object dimension, basically number of agents, maximum number of agents. Let's say that your model is modeling, let's say 400 or whatever it is. You have a time axis, which is like the future time that you want to predict. And then we have this mode axis, which is just to be able to predict different modes of the future distribution. So the way you can think about this cube is that essentially we are modeling the different hypotheses that we have for every object in the scene over time. And so each grid cell means our beliefs about the position at that time of that object for that particular future. And now we are trying to refine this in a refinement transformer end-to-end to basically get the detections as well as the predictions. So detections here are just the special case, basically t equals 0, right? If you think about the trajectory of the object over time. And this refinement transformer is consuming LiDAR from an encoder, LiDAR features from an LiDAR encoder and map features from a map encoder. And then we can run this refinement transformer iteratively for B blocks, and that can give us our refined detections and trajectory predictions. So let's see in a bit more detail how this works. So we extract LiDAR features like we saw in the previous session. That can give us, for example, multi-resolution tokens. So it's just multi-resolution features basically of the LiDAR in bird's eye view in this case. From that, we can initialize the poses, this volume that I was talking about, to maybe be, let's say, stationary object, like an object detector can give you an initial pose that can be the same pose over time for all objects. This is just a really bad estimate, but it's a starting point for the model to then refine it, as we'll see later. Then we have our high definition map. We run it through some lane graph encoder map, and then we get these sparse tokens, right, of the map. And finally, we can initialize also features on this volume to just describe essentially anything relevant to the motion of the object at that time. These are initially randomly initialized at the beginning of training, and they are just parameters basically of the network, these initial queries. And from here, we can go into this refinement transformer, which essentially is doing all sorts of attention that we'll talk a bit more detail in a second. And it's attending, I guess, both to the inputs, like the LiDAR and map tokens, as well as doing self-attention. And then we can literally just update the initial poses volume, right, and the queries. And at the very end, the poses volume will be our detections and predictions. Essentially, we designed an input that we are going to be refining, right? And at the end of this process, those are our actual predictions. So these are how kind of the attention works and the inductive biases that we bake in. For the position of the object at that time, or the position that we believe the object is, we can essentially do deformable LiDAR attention, which is an efficient attention mechanism that won't cross-attend to every token, but instead just cross-attend locally with some learned offsets. And we can do something similar with the map too, where we can just do, for example, k nearest neighbor map attention. That way we keep it efficient, and this kind of local reasoning allows us to refine the position of the object. And finally, we also can do self-attention. We factorize it because otherwise self-attention in this cube will be very expensive. So we do self-attention on each of the 3 axes of the cube. We reason about object interactions, about the different modes that we are predicting, as well as about time throughout the trajectory. And these are sort of what the model does. So initially, as I mentioned, we initialize it to be all stationary objects. And then after one refinement, it's already pretty decent at speed estimation, but you can see it has some map following problems here. And after another refinement, iteration equal 2, we still have some issues. But in the third one, the predictions get pretty good. by basically just attending to the local neighborhood um, of features. And this is basically at every iteration, we are refining. This is just over time. At every iteration, we are refining basically both the detection as well as the prediction. They are just because we are just refining this post volume that basically captures both. And most of the time for this section is for this last part here, which is about what are different, like actually prediction is kind of a very overloaded term. And there are many different tasks that one can formulate that kind of tackle similar problems, but not exactly the same one. And then there's also the representation aspect. Like, do we want to predict future trajectories? Do we want to predict the future sensor data? Or do we want to predict, for example, occupancy? So we'll cover all those. Maybe to start with something visual. So here what we are doing is we are predicting what that car might do. And we are saying it could be in these two places at some point in time, let's say 5 seconds into the future. And now if we try to answer like what the self-driving vehicle can do, really the only option is to kind of brake and go after the vehicle, right? And that's a pretty hard brake. But as we'll see now, like this is not how how the world actually works. How the world works is that these are joint rollouts, and the vehicle might yield to us, right? And we might go first, or the vehicle might accelerate and we need to go after. And you can see the futures for the two vehicles align with the futures for the two vehicles there. But the futures for the ego vehicle, like the self-driving vehicle, actually none of the two cases we had to hard brake as hard as we had to hard brake in this marginal prediction setting, which is basically telling us that that's not a great problem formulation, even though that's what most of the prediction models do today. So we can define multiple prediction tasks. This is the marginal prediction is what we had on the left, meaning that we are modeling each agent independently and trying to predict the distribution of each of them separately. Basically, you can see the color in yellow for one of them and in blue for the other one. We can instead model the joint distribution over different agents. So here you can see that there are joint samples, right? Like we have the pink future and the purple future. And these are joint futures across all the scenes. Basically, these are telling us the future might roll out in this way at a scene level or in this other way. And finally, we have conditional prediction as well, which we won't talk too much about, but it's also very interesting. Essentially, we have some power about what the future positions of the self-driving vehicle, right? We are controlling it. So we can try to condition the model on different future actions from the ego vehicle. Of course, you cannot be certain 100% of where your ego vehicle will do because you might change your plan in the future. So it is a very hard problem, but very interesting. Cool. So how can we represent basically these futures? It can be as trajectories. We can try to predict the future sensor data as well. We've seen many world models recently that do this. And we can also try to predict the future occupancy. So let's start first with trajectories. Kind of the simplest form of trajectory prediction is this mixture of Gaussian trajectories. It's a very simple parametric representation. We are essentially saying there are these k futures that are possible, and each of them is a sequence of bivariate, for example, Gaussians or Laplacians. And actually, if you take the negative log likelihood of this distribution and you try to train with it, it will actually not work very well. It results in mode collapse and instabilities. And what people have proposed are kind of mitigations around it by using this winner takes all loss, which essentially the idea is that because you only get to observe one of the possible futures, you only want to train from your predictions the closest one to it. So you are basically being optimistic and saying, if one of my futures is kind of close to the ground truth, I'm going to reward it. I'm going to train that mode. But the problem is that the rest of the modes are left untrained. So yeah, some of the modes at the end of training can be sometimes, if not very carefully trained, not good. Another option is to go with trajectory sets. So basically, we turn the problem from regression of trajectories and kind of the parameters of those distributions I was talking just now to a classification problem over a predefined set of trajectories. So here we can have, basically, we can try to get coverage from our sample set, which we maybe can get through clustering of our data set or just some parametric sampler that we can get. essentially, we are classifying over a fixed set of potential trajectories. One method that was very popular and worked very well and got a lot of state of the art in past years was this goal-based prediction. Essentially, you break down the problem into predicting first the hardest part, which is like, where's the vehicle going to be at the end of the trajectory forecast? Like that's what's called the goal typically. And then once you have these goals, you can predict how like the trajectory will complete from the current position to the goal and what's the score of that trajectory. So it's kind of an intuitive that you need to predict the goal first and to then predict how to get there. But if you think about it, because it's the hardest part, you can put more computation allocated to that, and then less computation allocated to predicting like the easier part. So I think that's kind of one intuition of why this works well in practice. But one drawback with this is typically goals are generated, let's say, from map nodes. So if you are trying to predict also non-compliant behaviors, maybe objects coming from unmapped areas, this can be a challenge for these methods. Another approach, which is similar to what I covered earlier with our work, DETRA, is this refinement based. So you predict some initial trajectories. They might not be very good, but they allow you to focus the computation around local areas and then refine these trajectories over multiple iterations. Cool. So these are sort of representations, generic representations that one can use for marginal prediction, for example. And the way marginal prediction is evaluated, let's say we are predicting these three modes, predicted scene 1, 2, and 3 here. And then this winner takes all loss that I was talking about earlier will basically take the closest mode to one of the futures, let's say the orange one for the top vehicle, and also the closest mode, the closest prediction to the ground truth future in black for the other vehicle, in this case, the purple one. So we are kind of mixing modes, different modes from different vehicles to get the lowest error. That gives you a proxy for after training for the marginal distribution. But as we saw, that's not great. So we can instead do this winner takes all loss, but at the scene level. So instead of considering the best mode for each object, you consider the mode that gives the scene level mode that gives the best average error across objects. In this case, is actually the green one, which is neither like of the two that we got in the mean FDE case. And by doing this, basically we can extend kind of trivially or pretty easily any marginal model into a conditional model. Like for example, for this model on the right, it literally takes the marginal predictions as input, like the different modes, and just predicts how to recombine them. Like basically it weights them different modes in a way that you can get new modes from a linear combination of the previous ones. And you train the first system, the trajectories on the left with the winner takes all at the agent level, and basically the ones on the right with the winner takes all at the scene level. Cool. But instead of just doing this winner takes all, which is a bit kind of empirical, like it's not really the true likelihood of the distribution, we can try to do something better. From the agent features, essentially, we can try to predict a latent representation of the scene, which basically this latent, you can think of trying to capture everything that is not in the sensor data. So, for example, you can think of this latent as capturing the intentions of the vehicles or the future traffic light states, which is something that we don't know about the scene. And then we can sample from this latent distribution. And given the sample of the latent and the input, we can run it through our decoder and predict one possible future. And we can do that many times and predict basically multiple different futures. And this can all be trained as a conditional VAE. And what this allows is to sample actually realistic futures at a scene level. So here what you can see is two samples from the model where essentially the model got at understanding that at an intersection, the traffic lights are controlling the scene. Even though it doesn't know what's going to happen in the future, it knows that the traffic light might stay green for the vehicles going north, or it might change the state and it might allow the horizontal traffic to flow. And this is very cool to see because the model wasn't trained with traffic light data at all. It just understood that at intersections, sometimes traffic light state can change, and then the whole scene changes. And because you have this continuous latent variable, you can also interpolate through it. So if you take basically two samples, which are the extremes of these GIFs, and you interpolate through them, you can essentially get this, basically latent interpolation, which is pretty cool to see that it can capture things like interactions at the bottom left, where you can see like basically if the lead object goes faster, the rear object goes faster too, or map understanding in the bottom right, where basically we can understand that it might turn left turn or do a U-turn. And here is kind of squashing everything together. So we are sampling 50 times for that joint distribution, and then putting them, overlaying them with transparency based on just the frequency of that position, and kind of displaying it as occupancy. And you can see that the model actually, for the time this was, which is 3 years ago now, or 4, I believe, it was a very good understanding of what might happen in the future. Cool. And more recently, autoregressive models have kind of made a comeback, I guess, after all the success of next token prediction with language. And there have been a couple of very interesting works in this in the last year or so. What these models do is that they basically predict future trajectories by decomposing the problem about sequentially predicting the future. So basically, I'm at time equals 0, I'm trying to predict the distribution over things that may happen at t equal 1. And then at t equal 1, given a position, a sample from basically the previous distribution I was talking about, you will basically predict a new distribution for t equal 2 and sample again. So this autoregressive sampling is very well depicted in this figure. Basically, we can tokenize the possible futures. That's what you see with the different objects. That those are basically tokens that the network can predict. So essentially, we are doing classification at every step, and we are trying to predict which of these different modes per time step could be the true one. And the good part of this is it breaks down the problem a lot. So you don't need I guess, as opposed to the trajectory sets I was talking earlier, where you might need thousands of trajectories to define or describe what might happen in the future. Here, you just need a lot less per time step, because essentially by having this very simple distribution chained over time, you can have very complex trajectories from a very simple conditional distribution. So this is very akin, to next token prediction in language. One of the drawbacks, of course, or the main drawback is that sequential sampling can be slow. Like at every point in time here that you're predicting into the future, you are trying to run, you're basically running some model. I guess it's all about how small can you make that model, but whether it can run real time or not, I think is yet to be seen. If this can be great for motion forecasting, but they are definitely very good for behavior modeling in simulation. Cool. So we've talked a lot about these trajectory prediction, but more recently there have been a lot of effort into world models that essentially predict the future sensor data. So let's look at it. This is a video from Gaia 1, which is a model from Wave, which had very impressive forecasting abilities. This is the model actually predicting the future for a pretty long horizon in a pretty realistic way. Of course, there are artifacts, small details, but it's very impressive, the performance of this model. Let's see a bit how that's done. So basically, video data is widely available. That's one of the main benefits of this type of representation that forecasts sensor data. So we can train, it's very super cheap to collect. You just put your vehicle out there and collect data, and you can just train from those future sensor data, right? And basically, it leverages advances in LLMs to tokenize the input modalities. Then all these inputs are fed into this world model, which is essentially a big transformer. And it's trying to predict tokens that essentially represent the future. These tokens that we predict in the future will be decoded by a video decoder in this case. But here, this is actually something that is great for let's say an offline model maybe, and definitely for a demo, but it's actually this could not be done online in our vehicle. Like that model I showed had about more than 500 tokens for every time step that you are trying to predict in the future. And it's basically auto-regressively predicting every single token. So for just predicting the next frame, it has to do 500 and something iterations of predicting the next token, right? And then that gives you the next frame, and you keep doing that. So it's very slow. It's not yet ready for onboard autonomy. And it's not clear how really to use it for autonomy, like maybe distillation, but that's something to be explored. We also had a similar work, but on LiDAR last year. Was presented at iClear, and basically here you can see the predictions for the actual actions that the vehicle did in the log versus like some counterfactual actions, right? Because these world models can be queried with alternative futures. Essentially, if the ego does this, what's going to happen? If the ego does this other thing, what's going to happen instead? And here you can see it in bird's eye view, where on the left, this ego vehicle is going with like a cruising speed. On the right, we are hard braking. And we can see that the vehicle, it's hard to see, but there are some points over there, basically behind the ego vehicle, that represent another vehicle. And you can see that how it reacts differently. On the right, it's basically following the ego fast, and on the left, and on the right, it's actually trying to basically brake behind the ego vehicle, right? Which is probably what will happen if somebody tried to follow. All right, it's a bit hard to see, but yeah, this is the points of the object. You can see it traveling over time, this cluster of points. And here, it's here. Cool. So this works actually in a similar way, but by doing some smart, I guess, design in terms of inductive biases, we are able to bring down the number of parameters very heavily. So the previous model I showed was a 6 billion plus parameter, and this model I was showing is under 100 million parameters, which is a very, very substantial decrease. And of course, this can make the model faster. We also, I don't have time to get into details, but we also use this discrete diffusion with parallel decoding, which speeds up a lot. Instead of predicting these 500 tokens one at a time, like I was talking about, you can predict, let's say, 100 on every step, and do that for 5 steps only instead of 500. So it's still, this is kind of a step in the right direction. It's also reasoning in 3D, which is closer to what autonomy needs to do, but it's still not fully clear like how to distill this to the actual onboard system. In general, my takeaway from this future sensor data is that there's a very open question about how to actually use them downstream. So let's now see the last output representation that we might consider, which is occupancy. I think actually this is a very good middle ground between trajectories and sensor data. So it's interpretable like trajectories, like we know what being occupied means and not occupied, whereas the color of a pixel or a point in the point cloud, it's a lot harder to interpret. But we can capture arbitrary shapes just like sensor can, as opposed to the trajectories, which assume this like rigid body, right? So let's say, yeah, and it's very easy to use in downstream planning because the downstream planner essentially wants to avoid any occupancy, right? Just to illustrate here, what we mean by this occupancy flow is on the top, you can see like a grid and what's occupied. And basically on the bottom, we can predict the motion also in a non-parametric way. This is not for every agent. This is just at the scene level. What's the motion? And then by basically, we can warp the occupancy with the motion to predict the future. And this have been applied even in this is a end-to-end driving model we had years ago. And it can do pretty cool reasoning. Like it can understand that this vehicle might go straight or turn left or turn right. Like you can see in that occupancy distribution, this pedestrian might cross the crosswalk or continue in the sidewalk. And it also can reason about uncertainty on the perception side, which is like on that area, we don't really see, right? Like it's occluded by other vehicles. So it can predict the occupancy over there too. I forgot to mention, but the boxes here are just the ground truth. The outputs of the model are the occupancy. So these still have several challenges, which are, first, they are pretty memory hungry. We talked a bit earlier about implicit architectures, but we'll review them again in this section. And then it's also label hungry. Like this is still trained with actual like labels for every object in the scene. And we'll see how we can train it out just from pure LiDAR in the future. So yeah, this essentially implicit occupancy fields that we saw earlier, right? Like we try to predict the future by basically getting a continuous query point XYT and the model outputting that occupancy and flow at those locations, like as seen on the right. So instead of predicting them on a grid, I mean, we can still predict them on a grid. We can just query XY for every XY point on the grid, but we don't have to if the planner doesn't need that. So intuitively, let's see how this works. So we have the scene, we have extracted our features, like let's say for LiDAR, and we are getting this query point at the bottom of the screen. So really, and let's say this is into the future, right? Like let's say we are getting what's going to be the occupancy there in 3 seconds. It's actually like the evidence for what might be there. It's not there in the feature map, right? It's wherever it was at t equals 0, not where the what we are interested at t equals 3 seconds. So what we do is that we predict an offset to basically we ask the model where to attend on the features to basically answer the question of whether this will be occupied at 3 seconds or not. And here in this case, it would try to attend to basically this object that is on the same lane, for example. So we took this intuition and we put it into a model. So we take LiDAR and map, we get some bird's eye view feature map. Then from that bird's eye view feature map, we basically get a query point over here. We can interpolate the feature map at the query point location. So let's say that point 3 seconds into the future, right? We just interpolate at the XYT location. And then we predict these offsets that I was talking about where else to attend in the scene. Basically, where's the relevant information to answer this query? And then we can cross attend to that, and as well as have this residual connection, which also brings the time, position, and encoding that we are requesting into this final MLP. The MLP predicts the occupancy and the flow for this query point. And we can do this for a batch of query points in parallel. Yeah, so these are the outputs. I showed something early similar in the previous presentation. That was just the unroll of the perception outputs over time. This is actually showing what we are predicting. Like basically, we are querying the model on a grid for the multiple different time steps into the future. So this model really unifies perception and prediction 100%, right? Basically, we have some features of the scene, and then we just have this time query that controls which time the occupancy we are getting is at. Cool. And yeah, the last part we'll talk about this unsupervised occupancy. Last year at CVPR, we saw a very inspiring paper, which is this 4D occupancy paper, which what they do is from historical LiDAR sweeps, they try to predict this future 4D occupancy, basically meaning 3D occupancy over time. Let's say you can imagine multiple voxel grids. And actually, we can differentiably render this into a point cloud, right? If you have the occupancy probabilistically, you can shoot rays and basically render where the ray would end according to the occupancy, basically depth rendering. And that, once we have that point cloud, that future point cloud can be supervised with just the ground truth future point clouds from the future. So this doesn't require any labels. Now, the specific architecture and loss function needed some work, and these works did not capture very well, for example, dynamic agents. Like it didn't predict very well the motion, even if it captured the occupancy pretty well. So we have this model that I just talked earlier, but basically we extended it to not just be able to perceive in the current frame, but being able to forecast in the future the unsupervised occupancy. So we can still use the same unsupervised task objective. Like for every ray, we can define an unoccupied and occupied area. And these rays do not need to be current rays. They can be future LiDAR rays that we observe from the log, right, during training. And by training with this sparse occupancy supervision that we get for free on future LiDAR point clouds, we are actually able to improve the results of this type of framework a lot. So on the left, you can see the initial baselines that kind of propose this framework, which are good at modeling the occupancy, but have a hard time modeling modeling the dynamic objects. And in the middle, we have this model that I was just talking about that we proposed where, we basically the occupancy we are predicting over time is actually over the future. And this is not a generative model. That's why you see like this spread of occupancy. We are actually predicting like what's all the potential occupied, right? Like at a probabilistic way, basically, instead of trying to sample one possible future at a time. Yeah, and then we can take this model that has been trained in a totally unsupervised way, and we can supervise it with ground truth labels. Let's say for something that we care about, like vehicle category or pedestrian category or anything. And what we see is that we can actually, this is on the x-axis you have in logarithmic space, the number of examples that are used for training. And we can see that a low number of examples, let's say under 100 especially, or even under 1,000, this type of basically unsupervised pre-training first with then supervised fine-tuning only on a few labels can give very, very, very substantial improvements, like 20 points MAP at 1,000 frames. Of course, this gap closes the more annotated data you have, but that's also very expensive to annotate that much data. I think these experiments are on Argoverse, if I remember correctly, and that 100,000 is basically the full data set. So we can see that even with the full data set of annotated vehicles, the unsupervised pre-training plus fine-tuning is still better. And yeah, this is just, oh, great, okay. I can play the video, but basically the middle, on the left is just the future LiDAR reference. On the middle is the 4D occupancy that the model predicts in an unsupervised way. And on the right is this bird's eye view occupancy that we were able to fine tune with labels. And so the model can do these different tasks. We also show in the paper that it can do point cloud forecasting by fine tuning as well, not just 4D occupancy forecasting. Cool. And yeah, to wrap up, basically, we talked about how to learn a rich representation of the scene from many different inputs like trajectories, sensor data directly, or high definition maps. We've talked a lot about how to model this uncertainty with different output parameterizations. And this is really key for basically safety and allowing the planner to understand the risk of different maneuvers. And we've seen that these joint predictions, sync-consistent predictions at the scene level, can lead to more proactive planning by basically better showing the planner like what are the different potential rollouts of the work. And yeah, finally, we've seen that occupancy, I think it's a great alternative representation. It can capture any shape and uncertainty like we can with sensor-based world models. And it can also be effectively pre-trained in a supervised manner and then fine-tuned for any task that we may care about. Yes, so that's the end of the presentation for the motion forecasting section. Thank you. Yeah, if there's any question, we can take a couple.
You explain how we use the folder and other type of model to predict motion. Wait, rail dots on that?
Hard rule on what, sorry?
Rail dots.
I
don't expect that sometimes this model will.
Yeah, so the question is whether, let's say for a learn-based system like Transformer, whether we have some guardrails to basically make sure that the predictions are realistic, right? Yeah, so I think guardrails can be good and bad. If you have a very bad model that tends to hallucinate, I guess, bad predictions a lot, then you might need guardrails. But at that point, it's also a question whether that model is worth much. And in the contrary, if the model is really good, I think guardrails can be detrimental because you might actually be predicting that, let's say, something illegal is about to happen. But then with your guardrails, you might remove that, right? So I think, yeah, in general, the best or the way I like to develop or I think about it is I think we should have as little guardrails as possible. I think we should have them at the system level, at the very final output of autonomy. But I wouldn't want to have these guardrails at, let's say, motion forecasting level where we are trying to predict the future in the best way possible. It would just, I think, limit a lot what the models can do. So it's more about, I think, having the right metrics and being very conscious of what's the level of, let's say, hallucination of this model. Should we deploy this or not? And rather than try to kind of fix it with some heuristics. Yeah.
No, that makes total sense. But for the full system level, we do have radars.
Yeah, if you're asking about Waabi, I guess I cannot disclose exactly what we do, but I do think it definitely makes sense to have guardrails at a system level. Yeah, we'll have a session on motion planning, so we can talk more about how those are designed. Yeah.
I think we can go to motion planning, and then right before the lunch break, we'll stick around for any more questions people have. Okay, let's do